Okay, we're going to talk about fluids, and in addition to what we've already talked about, which is pressure and buoyancy and density, we're going to talk about what happens when fluids move through something. So, right now we are largely interested in moving fluids. So, here we've got a pipe, that pipe next down, pipe's full of water. So, as that fluid moves into the narrow part, as it moves through this pipe or any other closed pipe kind of system, the volume of that fluid as it moves must remain the same. So the rate of volume flow of the fluid has to stay the same. If I get a gallon going by a second in the front part, I have to have a gallon a second moving by in the back part. If that doesn't happen, we're not incompressible. Something weird is going on. So, the volume there and the volume there have to be the same. You notice how that one's stretched out. That means something. As this fluid squeezes into the narrow pipe, it starts to move faster. As that volume has to push itself into something more narrow, in order to get the same volume per unit time, it has to flow faster through that part of the pipe. So the idea here, as the area of a pipe decreases, the fluid's speed increases. That's important. And the volume flow rate must be constant. So as the area gets smaller, the speed increases, and the volume flow rate must be constant. That's sort of our idea and our concept with that. And we want to look at the equation that goes along with it, because we will have to calculate this, more than just be able to explain why. So, what we're saying is that the volume per unit time in the front part, in the wide part, must be the same as the volume per unit time in the skinny part. Volume rate has to stay the same. Gallon in, gallon out. That's how it works. So what we're going to do is take volume, and instead of it being volume, we're going to take it as area times a distance. Area times x1, area 2 times x2. Because volume is the same thing as area times distance. We're just going to make a simple substitution in there. So our equation still says volume over time. We've just written volume in a different way. Now if we look, so that's x1 and that's x2. Already noticed that if the area gets smaller, that x has to be larger to make up for it. So it has the same volume. Now if we look at x over time, we know that position over time is velocity. So what we have here is area times velocity equals area times velocity. That's the area in the first pipe and the velocity through the first pipe. The area in the second pipe and the velocity in the second pipe. That matches with our idea. It's just that math, this is how it relates. So, as a pipe gets bigger, the fluid flow decreases. As it gets smaller, the speed of the fluid increases. We call this the continuity equation. And the thing that's continuous, or the thing that's going to remain the same before and after, is the rate of volume flow. And really, this only works for incompressible fluids. But good news, we're only going to talk about incompressible fluids in here. We're not going to worry about like air that we can actually compress, and it wouldn't really work the same way. So here's our big idea. In a closed system, the only way that we can change the speed of a fluid is to change the area of the pipe that it's going through. Moving up, moving down doesn't do anything. Changing the area affects the speed. That's the only thing that the speed is really going to depend on, is the area of the pipe. The area of the pipe is the same at two different places. The speed is the same at those two different places. Other things change, but the speed is going to be the same. All right. Closed system is like a closed pipe network. We don't have any open air spots for it to deal with. Now, when we change the speed of a fluid, we change the pressure that that fluid can exert on something. So, if we look at a still fluid, a fluid that's not moving, the fluid pressure pushes out. It can only push out on the walls of whatever it's in. However, if we get that fluid to begin to move, instead of just pressing out, the fluid is going to press on the wall at a little bit of an angle. So when the fluid moves, it pushes on the sides of the wall at an angle, which means it doesn't have as much outward push, and that means that the pressure decreases when the fluid begins to move. So we have a high pressure when that fluid can push straight out. We have a low pressure when it has to push at an angle, because only the perpendicular part on our tube really matters. The faster a fluid moves, the lower the pressure is going to be because of that. Now, the next part we're going to do is kind of talk about energy in this whole fluid flow thing. It's going to take a little bit. So, we're going to talk about work first. I think this is the toughest part of it, but it's not so bad. Now, our physics definition of work is that it's force times a displacement. So work is force times displacement. If I push something and move it, I do physics work on it. But we got to translate that into fluid work. So imagine that this is the cap or the stop on a fluid. And I'm going to push it. I'm going to push that cap a distance of delta x, and it's going to move that fluid through there. It's not compressing it. But if I apply a force on this fluid, and I move the fluid by delta x, I'm assuming all the pressure is going to be the same, I'm doing a kind of work. So, I know that work is force times delta x. That's fine. I'm sticking with that. I'm applying a force for delta x. Now, if we remember pressure, it's force per unit area. So I'm going to substitute the fact that force is pressure times area into that work equation, so it's in fluids language. I want to talk about fluids things with that. So I'm going to apply a pressure to this system as we move the delta x. It's going to make things move. So that work is now pressure times area times delta x. I just made that simple substitution. Now, I know that area times a distance is volume. So work here is going to be pressure times volume. I'm just redefining work in terms of fluids. So work over volume is another way of expressing pressure. Another way of saying that is pressure is work per unit volume. But that's going to allow me to talk about work in terms of pressure a little bit more easily. Work over volume is pressure. That's good to remember. Now, if we remember our conservation of energy, at any 2 points, the total energy on one side is equal to the total energy on the other. And the way we can look at total energy, just a second, the way we can look at total energy, at any given point, it's going to be the work that's been done on the system at that point, the potential energy U at that point, the kinetic energy U at that point. That's our possibility for energy at a given point in the system. And that's equal to the same sum of energy at any other point. They may trade how much goes in different places. So that's going to be work plus mgh plus 1/2 mv squared. That is work, that is potential energy, mgh, that is kinetic energy. Now, all of that is in regular mass language, and we want to get to fluid language. So we're going to do divide by volume so that we can kind of talk about a fluid now instead of an individual mass. And that's important because I have a whole fluid moving through a system, and I don't care about a part of that. I want to know what the whole fluid does. So if I divide by volume, look at what we see here. So everything is going to be divided by volume. Work over volume is pressure. Mass over volume is density. So we're going to make those substitutions. Work over volume is pressure. Mass over volume is density. So everywhere I see work over volume, I'm writing pressure. Everywhere I see mass over volume, I'm writing density. So this turned into, this turned into pressure at one point is plus rho gh at another point plus 1/2 rho v squared. All of those quantities are equal to the pressure at another point plus rho gh at another point plus 1/2 rho v squared at another point. So as we move around in a fluid in a closed system, this is defining how the pressure changes with height, how the pressure changes with speed. So let's just look at an example of what we can do with this. I got a pipe. Pipe is full of our water, just like before. And we have area 1 here that's 3 meters squared, area 2 that is 1 meter squared. It's going at 5 meters per second there, and it has a pressure of 110,000 pascals. That's all the information that we have. And I want to answer 2 questions. Find the velocity in and the pressure through the smaller tube. I want the velocity in the smaller tube. I want the pressure through the smaller tube. So let's look at the velocity first. Speed first. Here we're going to use the continuity equation, or the idea that as the area gets smaller, the speed has to go up. So area 1 times velocity 1 equals area 2 times velocity 2. So all we're going to do is plug in our numbers for area and velocity, and then solve for velocity 2. In this case, velocity 2 comes out to be 15 meters per second. So my area reduces by 1/3, and my velocity goes up by 3 times. That's important. Now let's look at the pressure. To do that, we have to use this whole big equation, and you're going to get this whole big equation every time. So for pressure, since the speed increases, we know the pressure has to drop because it's not pushing out anymore. So looking at this system just in general, if the speed goes up, the kinetic energy has to increase. So we know that piece is going to get bigger. The 1/2 rho v squared piece has to get bigger as we go through this. The potential energy doesn't change because the height doesn't change. The center of my tube is at the same height in both places. So if the kinetic energy part goes up, then the work or the pressure part has to go down. That's what we're expecting. So let's put it into this little equation. We got to write the whole thing out. But height 1 and height 2 are the same, so we can cross those guys out. That simplifies this to pressure 1 plus 1/2 rho v1 squared equals pressure 2 plus 1/2 rho v2 squared. Now we're going to plug in all of our numbers and solve for P2. That's all we have to do. We're going to put in the density of water, 1,000 kilogram meters cubed, and the velocity at one part, density of water, and the velocity at another part. So we're going to take 110,000 pascals, add to it 1/2 rho v squared from the big pipe, and subtract 1/2 rho v squared from the little pipe. Now, what we see here is that the 1/2 rho v squared part went up, and we expect the pressure part to go down. Let's see what we get. And you can do this math on your own too. When you put it all in there, pressure 2 comes out to be 10,000 pascals. That is a big drop in pressure because we had a big boost in velocity. We'll do more videos later with a couple more examples, but this is all we need to know for right now.